Throw you in the choke, gun smoke. Biggie smoke for mayor, the rap slayer, the hooker layer, motherfucker say your prayers. Hail Mary, full of...
Hello and welcome to the video on approximating and computing area. Okay, so first we're going to start with, let's say we have a graph of something at constant velocity. Okay, so this is a constant, and this is our v of t graph, and this is our t. Okay, so here's velocity, right? Let's say if we measure from t1 to t2, how far did it travel? If we draw our lines here, so here we have from t1 to t2, it was traveling during this time period here, this interval, right? So t2 to t1, basically, that's how much time it was traveling for, and at a constant speed, which was c, or we can name it v, okay? In this case, because our velocity is constant. So we see v times the change in t, so v times change in delta, delta t. So this is equal to the distance traveled. Distance traveled. And this also happens to be, so here's our v value, or our c, our constant value of the function v, and this is t2 minus t1, which is the same thing as delta t. So we see that that is actually the distance traveled is the area of this, it could be a rectangle, it doesn't necessarily a square, but this rectangle under here, that is the area which represents our distance traveled. Okay, so now let's look at a little bit more complicated graph. So let's say again we have like time versus, or velocity versus time graph, okay? But now we have a velocity graph that kind of jumps around at certain intervals, okay? So something like that. And let's say we want to measure from t1, from here, up to t2, okay? So if we draw our vertical lines upwards, then we'll actually be measuring, under the other one, it was the area of one rectangle, but under here we'll actually be measuring the area of 3 separate tall rectangles. But this also will give us, whenever we have, this is, so the distance is going to be the area under the graph. So those 3 triangles I shaded in from t1 to t2. So under the graph, okay, graph of velocity over the time interval t1 up to t2. Okay, so that would give us the area there. So this is like the basic layout of where we're going with this. So that, again, so distance is velocity times time, okay? But that's only at constant velocity. So when we get an even more complicated graph, and by more complicated, I mean like a curvy one, right, where it's not really that easy to draw rectangles underneath. But let's say now we switch into x and y, our normal x and y axes there, and we want to measure the interval between A and B, let's say. So even though this is a curvy graph, we're going to still approximate it using rectangles, okay? So we're going to use rectangles to approximate, all right? To approximate the area under this curve, approximate. And we're going to do so on the interval from A to B. That's our x interval. Okay, so what we're going to do first of all, so this is our f of x. That's our function. And what we're going to do first is, so here's our entire interval from A up to B. Okay, so we want this entire area under that curve. So what we're going to do first is choose a number called capital N of how many sub-intervals we want. So sub meaning like mini intervals inside of our AB. So this is the entire interval, AB, that's the one that we're studying, but now what we want to do is break it up into pieces, okay? So our full interval is B minus A, but now what we want to do is break it up into N pieces. So let's say we pick an N, okay? So therefore, the change in X for each of these, so let's say we say that we have delta X, okay? So delta X is actually going to be the length of our subinterval. So length of our subinterval. And that's basically going to be the entire length. So our full length of the interval divided by whatever number we chose, however many subintervals we're going to make, okay? So this is equal to the change in x, how much we're moving on the x for each subinterval. So this one, if we move a delta x distance, delta x to the right, we're going to get that this new point is a plus delta x. And then the next one, if we move another delta x, then this point is going to be a plus 2 delta x, right? Because we jumped twice we jumped 2 delta x's lengths. And then we're going to keep going, etc., dot, 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 until we get to b, okay? And then b is equal to a plus an n delta x. And n was how many subintervals we were going to do, okay? So we did 1, 2, etc., n subintervals. Okay, so now that we've identified the points within the interval, I'll continue this approximation on the next slide. So we have the graph. So here's our x, there's our y, and I'll continue, I'll redraw this really quickly. So we have our a, our b, and then we have a plus delta x, a plus 2 delta x, etc., dot, 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 until we get to b, which is equal to a plus n delta x, okay? So in each of these intervals is the length of delta x, all right? So that's delta x, etc., etc. Okay, and this is our f of x graph, all right? And our delta x is equal to b minus a, so the length of our full interval divided by however many subintervals we do have. Okay, so what we're going to do is start with, because what we want to find is the area under this curve, under our f of x curve, right in this interval a to b. Okay, so what we're going to do is start with what's called a right endpoint approximation. Okay, so right endpoint approximation, and I'll abbreviate approximation like so. Okay, so this is kind of, it's self-explanatory, or it gives it away, right? So we're going to do a right endpoint. So that means for each of our subintervals, so for example, this is one subinterval here, we're going to pick the right endpoint of it. So this one right there. So for the first subinterval, we're going to pick a plus delta x. That's our x value for the first one. For the next one, we're going to pick whatever's to the right of that interval, so that would be a plus 2 delta x. And we're going to keep going, so on and so forth, until we get to a, and the last one is going to be b, which is a plus n times delta x. Okay? So, this list here that I just drew, these are our right endpoints. This is our list of right endpoints, okay? And now what we're going to do is actually draw a straight line up to the graph, which is the equivalent of evaluating our function, our f of x, at each of these right endpoints. Okay, so I'll draw that down there on the bottom. I'll show you guys. So we have, if we plug this into our f, we get f of a plus delta x. And then for the next one, we get f of a plus 2 delta x. So for example, this would be the point up here. This one is f of a plus delta x. This one is f of a plus 2 delta x, etc., etc. Okay? And then we're going to go all the way up until we get to f of a plus n delta x. That's a delta, not an a. Okay? So once we get those, then we're going to, from here, we can construct our rectangles. Okay? Remember I said we're going to be approximating with rectangles? So here on our graph, we're just going to draw straight across. So for this first interval, this is the bottom. And then this is the height, because we measured it from the right endpoint. Okay? Then we're going to draw a line straight across to the left line there, and draw our line straight down. So this is one rectangle. The next rectangle for this interval is given by the bottom, and then the right endpoint gives us the height, and then we draw straight across. So those are kind of similar. But now for this next one, we have our base, and the the height is given by the right side. So then we draw our line straight across. So this one's a little bit taller, right? And then our final one for this interval is going to look like this. We're going to draw our line straight up and get the height, and this one's even taller, even taller than the third rectangle. So now what we need is the area of each of these rectangles, okay? So we'll do that on the next slide. So the area of this first rectangle here that I'm shading in is going to be base times height, right? So the area of our first rectangle, rectangle number 1, that's going to be base times height, and the base is a length of delta x, right? Because that's the length of our subinterval, so we have a delta x times the height, which was given by the height of or the value of the function, our f of x, at this right endpoint, which is a plus delta x. So the value of our function at a plus delta x, that gives us our height. So this is height, okay, and this is the base of our rectangle. So for rectangle number 2, I'll shade that one in. So then we have this one right here. Of that rectangle, we also have the same base, right? That's just the length of our subinterval, and this time the height is given by the right endpoint. So that would be f of a plus 2 delta x in this case, right? So then we have that point down here, and we're evaluating the function there. All right, and we'll keep going along, keep going until we get to this last rectangle, which is the nth rectangle. And this is, again, same base there, same length of the base. Then we have f of a plus n delta x. Okay? So what we're going to do with all of these rectangles once we compute them is add them all up, add up all of their areas. Okay? We're going to add them up, add up. All right? So what we're going to get is that r sub n, which is, this signifies the nth right endpoint, approximation, okay? Approximation. This is going to be equal to, basically, delta x times our f of a plus delta x, okay? And then plus, I'm just going to factor out the delta x from all of them. This is representing all of them. Okay, and then I'm just going to add everything else. So a plus 2 delta x, and we're just going to keep going, a plus 3 delta x, etc., until we get to f of a plus n times delta x. Okay, and then there are 2 parentheses at the end there. All right, so this is our nth right endpoint approximation. Okay, and because that looks a little bit long, we have a different kind of notation called summation notation. That kind of rhymes, sort of. Has a little jingle to it. So what summation notation is, it allows us to rewrite the long thing that I just wrote, like the r sub n thing, as a pattern series. Okay, so it allows us to rewrite it as r sub n is equal to, and I'll tell you what all the symbols mean. So this thing, it's a sigma, that means sum of. Okay, so sum of, so that means we're going to add up everything from j equals 1 up to n, and I'll show you where that goes. Of delta x, and then our f of a plus j delta x. Okay, so this thing, again, like I said, that means sum of, and then this means these are the endpoints. These give us kind of like the interval or range, interval/range of j, of the variable j. Okay, so that's what it could be. J ranges from 1 all the way up to n, using counting numbers. So 1, 2, 3, 4, all the way up to n. And then this thing here, whatever we see after the summation symbol, is basically the formula, okay? So the formula of how to obtain the terms to be added. To obtain the terms to be added together. To be added together to each other, okay? Or to be summed, basically. All right, so this is basically going to be equal to, so let's say we take out this delta x, because that's going to be the same in all the terms, right? So r sub n is equal to delta x, and then we have this sum of j equals 1 up to n of f of a plus j times delta x, okay? And then this is basically going to be equal to whatever we had before. So this is equal to delta x times, and we're going to add them all up. So f of a plus, and j starts at 1, so 1 times delta x, plus f of a plus 2, this is the next j, plus all the way up to f of a plus n delta x. Okay, so that's basically what we had before, right, for our nth right endpoint approximation. Okay, so now that's the formula for right endpoint, and now let's do the one for left endpoint approximations.
With this like Kumacho, I got soul, but now I should be down with the stylistics. Make up the break up, niggas need to wake up. Smell it, Indonesia.